Hi folks, Mr. Long here. We're going to look at how to develop equations for these trigonometric functions that are based on turbines that use wind power to generate electricity. And so we're going to look at number 4 from the work that was assigned, and there's a couple of things to address here. Actually, two specific things. The first thing is you may have received a copy of the handout that has 10 instead of 100 here. So it should be in the question, it should have said 100 meters, not 10 meters. That's the first thing. If your handout has 100 meters, you're fine. The second thing is in the solution set, I use the period as 64 seconds. So the time to do one full revolution, but so that's in the solutions. But the reality is, if we look, it's 120 seconds for 2 revolutions. So it actually should be 60 seconds. So your answer, the answer that I provided, is going to be a little bit off. But I'm doing this screencast for number 4, and so hopefully we get everything correct here. Let's hope anyway. Okay, so what is this question about? What are the things that we need to know? Well, I think it says that the blade length is 160 meters, right? So if we look over here, and I apologize for how busy this diagram is, but the blade length is the amplitude, which is also the radius of the wheel. And so that's 160. Q, which is the midline, okay? And that's a distance from the ground right here all the way up to the middle, okay? So I've got to go 130 meters, the base height, and then I've got to go a radius, a radii, which is 160 meters. If I add those two together, 160 and 130, I get to the midline. The midline is 290. Okay, the maximum y value. So what is the height at the top of the wheel? So it's the 130 plus twice the radius, or the diameter. So, or Q, 290 plus that distance from there to there, the radius, or the radii, which is a radii is plural. So the radius, 290 plus another 160 is 450. So at the top of the wheel, we're 450. So we have all of those things. Oh, by the way, the period is 60, and we know that K equals 2 pi over T, so that's 2 pi over 60. Now, let's start to take a look at the hard part here, which is the phase shift. So how are we going to measure time? Well, what it says is we're going to measure height from the ground if time starts being measured 100 meters below the maximum on the way down. So we know that we always rotate in this direction counterclockwise. Okay, so we always assume that for mathematics. Even if it rotates the other way, we're going to assume it's rotating this way. So here's what we know. We know that the top is at 450, and we're going to start measuring time when it's 100 meters below that maximum. So here's 450, right? There's 450, and then we have to drop by 100 meters. So from 450 to 100 is 350 meters. So we're going to start measuring time when the wheel, a point on the wheel, is at 350 meters above the ground. So it's very clear that because that's 290, the 350 is in this quadrant right here. So I'm in the top left quadrant, and I'm rotating down. So if I look at this, I'm from 350 to 290 is 60 meters. So that distance is 60 meters there, and this distance is 100 meters. So what am I closest to? Am I closest to this positive cos, rotating from the top, or am I closer from the midline, rotating down? Well, I'm pretty sure that since that distance is 60 and that distance is 100, I'm closer to right here. Again, it doesn't matter. I can use a cos curve, a negative cos curve, or I can use, in this case, or positive cos curve, sorry, or a negative sine curve that's shifted. So I'm going to use a negative sine curve. So how much is it shifted by? That's the big question. Well, let's take a look at it. So I'm going to take this triangle right here, and I'm going to draw it over here, because I have to figure out what this angle is right here. Because that angle, which in fact represents time in seconds, right? I have to figure out how much time before it reaches 290 is that location, right? So let's take a look at what that triangle looks like. So let's zoom in on that triangle. So that triangle right here, okay, so that the very top is at 350. The bottom of the triangle is at 290, that's the midline, okay? And this is the opposite side, okay? And that radius is 160. So if the top of the triangle is 350, the bottom of the triangle is 290, then we can tell that the distance from here to here is going to be 60 meters. Okay, so if I want to figure out what this angle is here, I then am going to use sine, which is opposite, over hypotenuse. Okay, opposite divided by hypotenuse. And I'm going to figure out that angle. Now that angle is actually going to just be in radians. Okay, so it's going to be sine inverse of 60 over 160. And that's going to tell me the angle in radians. So if I do that, I end up with this right here, 0.384 radians. Okay, so that is, if I think about it from the perspective of, let's go back to this, if I think about it, that means what fraction of the circle is that? So I'm going to just use this color here. So I've got to figure out what fraction is that part of the circle relative to the whole circle. Okay, so that's what I've got to figure out. Because if I can figure out what fraction that is, then from there I can get what fraction of the period of 60 it is. Okay, and that's going to tell me how many seconds it's in that pink area. Okay, how many seconds. So let's go back down here and take a look at this. So it's 0.384 radians. Well, here's what I know. So what fraction of a whole circle is that? Well, it's 0.384 radians out of 2 pi. This is no different than saying it's, because, you know, what is 0.384 radians? Well, 1 radian is 57 degrees. So that's maybe 25 degrees, something like that, right? So that would be like saying 25 degrees out of 360. So I'm going to say 0.384 divided by 2 pi. Now that's the fraction of the circle that we go through in that interval. Now I have to multiply that by the period, by the 60 seconds it takes to go around the whole circle. Multiplied by 60 seconds, which is t. I'll just put the t underneath that to help you. So that tells us how many seconds we're in that small angle. And what it works out to is 3.67 seconds. So let's now try and figure out what our equation might be. Okay, so I know that f at 3.67 seconds. So let's go down here and think about this again for a second. So I'm going to go to this where I know it's very busy. Actually, you know what? I'll draw it down here. I'll just draw a separate one. So here's what I know. I've got my circle here. I know that angle is 3.67 seconds. Okay, and it takes 3.67 seconds to go from where we're measuring 0 seconds down to here, which is now 3.67 seconds. Okay, so what do I know? What is the value? What is f at 3.67? Okay, what is the height right there? Well, it's on the midline. And what is the midline? 290. So f at 3.67 is 290 meters. Well, if I'm to have that at 290 meters, that means that this is the only thing I'm allowed to have. This whole part here must be worth 0. Okay, what's the only time sine is worth 0? If the angle is worth 0. So what do I need this to be? Well, it needs to be x minus 3.67, right? Because it'll be 3.67 for x minus 3.67. Okay, the other way to think about that is it's 3.67 seconds behind, because rotations are positive in that direction. So the rotation started 3.67 seconds before the natural start of a negative sine curve. Okay, so that is our equation, x minus 3.67. And that will be our formula. It's negative sine because it started in the middle and rotates down. Okay, folks, so I know those are tough ones. That is the toughest type, and I tried to explain it in as much detail as I can. All right, so hopefully you've got an opportunity to work through the rest of them. Best of luck.